Hello, hello.
Good afternoon.
Good afternoon. Thank you. Good afternoon. Oh, a lot. Oh, there's so many more images on my screen than there were in the an hour and a half ago in the other class. I'm so pleased. It's so colorful. It's so not black boxes. Good morning. Good morning, Amber. Good morning, Alan, Nelly.
Good
Good
morning,
morning.
Professor.
Good morning. Thank you. Oh, that's cool. Good morning, Sarah. Good morning, Wenyi. Good morning, Andre. Good morning, Armand. Good morning, Alyssa. Good morning, Jenna. Thank you. Good morning, um, Sarah. I said good morning, Kimberly. I said good morning. Oh, more people coming in. I know this is so cheesy that I do this, but it's like my favorite part of the class. Anyway, um, and good morning, Armand. Good morning, Erica. Good morning, Sheeran. Good morning. Who? And also, this is a way of, as I keep butchering some people's names, you can subtly tell me in the private chat or whatever. I still feel bad about that. Good morning, Marissa. Good morning. Who else we have? Alyssa. We got Rachel. Good morning, Armand. We said, I think. Good morning. Who else? Okay. Good morning. Good morning, Sharon. Thank you. And good, I think that's good morning, Alea. Good morning, Abby. I think that's okay. I think that's everybody for the okay. Anyway, hello, hello. So we're getting more and more into physics. I'd like to get even more each day, hopefully getting more quickly just into the material. I think you guys are doing great. Like, I think you're all on top of the homework. And I hopefully you've gotten everything back that you've done. We're gonna, there's not new, if you have done, and most of you really have, you've done a ton of the math methods sheet, I mean, all of it, most of you, and um, and the sheet number one. So you're not going to get a new sheet for a little while. Like, that's the good news, is I know now I'm fully behind you guys in every good way. Like, I've seen what everything you've done on these sheets, and now we're talking about in class. So I'm aware, like, we're still at the end of sheet one, um, with this little side road thing, and then we'll get to sheet two. So no new homework for a little, at least for tonight. I mean, there's not, other than the game stuff and blah, blah, which everybody seems to be doing great with, or I think everybody's understanding, which is great. So, so that's good. Like we're here to now start really going through this and unpacking this material. So where we were, so I'm going to dive in basically is what I'm saying, but I really I want to, once again, just want to say I'm very pleased with where you guys are and what's been happening both in the class and in your work. So I'm going to get rolling, but please stop me. Please, it's still the same thing. Like, if you have any question, oh, good afternoon. Awesome. Oh, sorry. Yes, good afternoon. Okay. Um, but if you have, I'm going to just get going to where exactly we were last time, mathematically, like in the notes and everything. But anybody should or could stop me at any moment if I'm leaving behind something about homework or grades or administration stuff or the physics. Like, please do stop me. But because I'm assuming that you will, I am just going to step forward here and start and pick up where we were last Wednesday. Oh, and there's something in the chat. And where we were last Wednesday was, oh yes, um, where we were last Wednesday was we were doing this kind of practice calculus problem on its own to the side in order to really see what's going on in question 9 of homework 1. Now, and that's what we're going to continue right now. Hopefully many of you realize, since you've done math methods, homework number 2, which we have not gone over yet, hopefully you sort of see a connection between the first set of exercises in math methods. Like, we're kind of looking at the same thing here, which is derivatives. Um, and it, yeah, and it's unavoidable. This is where physics goes at this point. So we're still in sheet 1. We're still, and again, stop me if with whatever, but I believe we are. Okay, I'm telling you again, and at the risk of redundancy as always, but in the here's where we are in the class. Like we looked at a mass, sorry, in the class. Sorry. The physics of this is we just have a spring with a mass on the end of it. We write down what we know about the physics of that. And it's two physics statements, F net equals ma and F equals negative kx. We put them together and then we have this mathematical statement. Okay, the physics brings us to this mathematical statement. And due to physics, we want to solve this mathematical statement. Now I have to, and that's all our work right now, all our little digression. I mean, it's not really, but our little like sidebar thing that we started on Wednesday. And this entire math methods homework assignment, which you could say is like one big sidebar of like mathy things. It's all really because we wish to solve this equation. And the truth of the matter is, at this stage of our lives with calculus and whatever else, I think that for someone to write down this statement and say we solve it now is a very slippery new, like I think to most of us, it's not even clear what it would mean to solve this equation in the first place. Oh, sorry. Hold on 1 second. I'm sorry. 1 second. Okay. 1 second, everybody. Just 1 second here. All right. Sorry. I thought that was life, whatever. What I'm, there's something. Oh, I see. Okay. Hold on. Sorry. Okay. The quick thing that I just want to say, so our whole exercise is to solve this mathematical equation. The thing is, and it's real math. It's real math. I want you all to know that. But that's why I like teaching it, because it's real and you'll all learn it. It's real in the sense that we're going to learn how to do this math. We're not going to try to remember how to do this math from other math classes where we might or might not have understood what was going on. We're going to do this like physicists do it, which is figure it out. But what's important is to know what our goal is. When we say we wish to solve this equation, right? Like that is our physics goal. And it takes a while. Like, I mean, it's a big focus of this course, weirdly. But when we say we wish to solve it, it's very, like that bothered me a lot for when I was a student, because I'm used to thinking if you want to solve something, that means you want to get a number or something. And I was like, well, all right, solve it once, get the number, and then can we move on? Like, why is it this big undertaking to keep solving the same equation? What we mean when we say solve, please remember, what we mean to solve something of that form means to find an x as a function of t, right? We're trying to rearrange it to get x by itself, in effect. But because x is locked into derivatives there on the left side, it makes things more tricky than regular algebra, right? So that's the context here. So then what we said last Wednesday, where I want to bring us back to is last Wednesday, we did one example. Well, I'll just quickly write, but now today we're going to do a different, we said we were going to do an example of contrast. Last Wednesday, I said, right, this is just quick review or just this a reminder. This is what we found in the last class. And again, just to remind you, sorry. Just to remind you, we did this exercise just to remind ourselves, or just to review, what do we do when we're given some equation that has x's and t's in it, but the equation makes reference to a derivative. Like that's all this is an equation that has a derivative in it. And note, it's a first order derivative, like it's a first derivative, derivative number one. And so we solved it. That was an equation that had a derivative in it, and it wasn't a second derivative. And also, I'm just saying that was an equation that had a derivative in it. What we're meant to contrast it with is what we're going to do now. So that's what we did. And you may or may not remember how we did it, but that's what we did Wednesday. What we're going to do now, and I can turn that back if anybody wants or whatever. What we're going to do now, sorry. Yeah, what we're going to do now and maybe I said to think about this for homework, but whatever we're going to say, consider this. And I think I changed it doesn't really matter what number you put here for number two. I may be inconsistent about it. But now we're going to consider the same thing, the same kind of setup. And we're going to try to solve it by the exact same method. I'm going to ask all you guys, maybe some of you did it already, but I'm going to ask you to turn to your notes from Wednesday and get a solution to this. Again, we're looking for x as a function of t. Like we're looking, so something like x equals 5t squared over 2 plus 7. And I know a couple of people did get this in the class last time, I think in private chat, and that's okay. But nonetheless, I'm saying now we're going to get the same, we're looking for the same type of thing, some x expression. But now the one major change that I've made, I mean, it's a subtle but major change, is I'm giving this thing, with all that I've changed is on the right-hand side, instead of a t, I put an x, but I want to make it clear to everybody that this is now becomes by changing that t to an x, we are changing the character of this expression and making it into what we call a differential equation proper. This is, in other words, again, just because something has a derivative in it, it might be intimidating, but that doesn't make it a differential equation. if something has a derivative in this particular way, then it's a differential equation. And then we have to think about what we're doing with it. And all of physics really is ultimately about this. So I'm going to pause. I'm going to say, unless there's something to, oh, cool. Wait. 1 second. And just looking at a couple things in the private chat, I'm even going to say, I don't mean to confuse people, but just to make it even more concrete, I'll even leave the, you could do it either way you want. It's not, but just to, because someone just made me realize something in the private chat. Let's even just leave this. I'll even leave this as 7 as it was before. Again, you could do it either way. I don't want to change people's minds midstream, but I would like, so some people have already gotten this, but I would, right, yes, exactly. If, hold on, very good. Someone just put something. Yes, by changing, in other words, if I change the value of x at t equals 0, that's only going to change the constant of integration. And in fact, yes, that is part of what I want people to see. And so if you just wrote that in the private chat, you're totally right. And if you don't see that yet, you will. Hold on, but where did that person go? So I'd like everybody to try, do the exact same method they did on Wednesday and just try to get an expression here of E. And if you've already done it, just hang tight for a second. I appreciate it. But yes, let's all try this. And maybe, especially those of you who are doing it right now, who are doing it now for the first time, feel free once you get any thoughts at all. I mean, put in, if it's a final answer, maybe put in the private chat if you wish. But if it's a question or a thought, put it in the regular chat. But this is what we're trying to do right now. This is the do now. Oh, cool. Okay, I'm looking in the chat. So I'm getting some really good things, and I'm taking my time here, or taking your time, because slowly but surely people are progressing, and I'm getting things in the chat. I'll admit to all of you, I'm getting enough things in the chat to keep me wanting to wait here before we go over this. I will admit that most things I'm getting in the chat have a mistake in them, like, which also just means that this is worth doing to everybody. Like, no one is crazy and everybody's on page, but I'm going to wait for a little bit to go over this, because I think you all do want, you're all right to think in terms of antiderivatives and integrals, but look really carefully at exactly how look at what we did on Wednesday. Excuse me. Like, look at the line. If you took notes, like that, it's often the case that the very lines that I add that seem the most unnecessary, the parts where I add where that seem obvious or that you could skip them, are often actually the juicy lines. The second line we did on Wednesday is what a lot of people are either skipping right now, or they're doing a little bit carelessly or something. But you guys are right to want to integrate something or to anti-differentiate something. But to know what actually to integrate or to anti-differentiate, look really carefully at, like, at this, and see what we did on Wednesday. Like, we don't just take the integral of both sides of that. We can't do that. It doesn't make sense. You can't take the integral of dx over dt. And you can't take the integral of something that doesn't have a dx or a dt in it. So we have to do something to that first line to make both sides integrable, and then we integrate. I'm just talking to everybody here, but just based on what I'm seeing in the chats. I did get one, I have gotten some right answers in the chat, but I've also gotten enough misguided things that just, I think this is worth. And do remember that, oh, I'm looking at the chat. Remember, I am saying the whole different, whatever we did Wednesday, we had T on the right side. Now I'm saying All the difference in the world comes from the fact that it's an X on the right side. And not that, I mean, both of those letters of the alphabet could be used for whatever we want to use them for. But the fact that T is being treated here as the independent variable and X is the dependent makes all the difference. So just be careful about that X. But all right, I'm looking in the chat. Oh, okay, cool. Oh, I know. Okay, still going to give you, I know, sorry. Okay. I'm going to, in a minute, I'm going to ask if anybody does want to give a stab, or I'll go over it. Like in a minute, we'll stop thinking. But just as a reminder or another perspective here, like we're looking for functions when we are given their derivatives. So sometimes it's easier than other times to find the function. Like Wednesday's example was maybe a little bit easier than today's example of how to find the function. But once you find what you think might be the function, however you find it, oh, I just lost, sorry, however you find it, you can find out whether you're right or wrong by checking. Always. Like finding the function is hard, but knowing whether it's right or wrong is always straightforward, because all you have to do is differentiate and see if you get back to the original that you were given. So you may never know exactly how to get your answer, but you can always know, once you have something to play with, whether it's right or wrong. So it's often helpful just to sorry. Sorry. Okay. Okay. It's looking. So I'm going to. Does anybody? All right. I want to go over the right way to do now this question. As I say, an answer or two in the chat is correct, but I don't know. But so ideally, someone would volunteer to talk this if they. Well, does anybody want to? No, let me ask this. Could I get a show of hands? Is it clear that we're on? Is it clear what problem we're on? And is it clear? Raise your hand if it, sorry. Raise your hand if it's clear that someone's about to go over the solution to this problem. That's one person. Okay, thank you. That's two people. Okay, it's not even clear to me. Thank you. Three, four, okay, a bunch. Oh, thank you, Aaron. Thank you. Okay, okay. So that's clear. So if anybody wants to be that great. No, thank you. I totally appreciate it. Okay, I feel like I'm losing my. Of course, I think it's always better if it's somebody who's not me. But I'm a little bit. I'm getting the sense maybe it should be me on this one, unless somebody wants. Actually, I think it is going to be me. All right, I'm going to show you. This is what I have in mind for how to the answer to this problem. Someone did put in the chat, at least the answer does have an E in the answer. It is like e to the 5t. It's like there's an E in your answer. If you don't have an E in your answer, something is wrong. But let me show you where the E came from. Okay, so this is what we're, so here's the problem again, just to be clear. All right, and I'll leave it as 7. I keep being inconsistent what that X naught is, but so here's our problem, right? Now here's how to solve it. The very first step, like we're trying to solve this business right here. We're trying to solve this. The very first thing we should do is not integrate. The very first thing we should do is the very first thing we did on Monday and say this. Right. And I did see in the chat, some people actually did do this, but just know if we're super careful, like we now have dx equals 5x dt. Now we did this so that we can integrate eventually, but we're still not quite there. We still have a little, like we're almost there, but now we have an issue because we have on the left side is integrable, so to speak, but the right side doesn't make sense because t is the variable of integration according to that right side, and yet x is a variable sitting there. So what do? Well, we could do something like this. Now this is now, right? I mean, I'm leaving the 5 there on purpose. You could take the 5 with you. I think it's a little bit easier not to, but either way, that's valid. And now we have all the x's collected together, all the t's collected together. Now I'm just going to recopy that exact same thing, but now it's integrable is my point. And it really wasn't before then. You really can't just, so anything, you can't do the integral of 5x or something because it's with respect to the wrong variable. So we could do this. I'm just recopying. So now I can say, okay, well, I'm going to integrate both sides. And I'm really trying to say that I really could not do that before. Like the integration is what we want to do, but we're only allowed to do it if we're allowed to do it. So now I have this. Now I can say, okay, on the, well, I'll stay. I don't know why. So on the right side, on the, okay, on the right side, we get, actually, could someone tell me what do we get on the right side? Yes, thank you. Thank you very much. Yes, and you are definitely paying attention. And I know that you, the person I'm talking to, is probably bored at this point, but I totally, yeah, hold on a second. Yeah, but yeah, yes, good. That's okay. That's a lot of, great. Both of, if you just direct messages me, yes, I totally, and I'm not going to direct message back, but yes, that's awesome. So we get, well, and in fact, well, let me actually be a little bit more, yes, but in fact, really, I should say this, right? I mean, is everybody cool with that? Like, that's the right-hand side. If that's an indefinite integral, I mean, that's what it is. Now, what, and I'll just move this down. What about on the left-hand side? Does anybody want to tell me what's going on? Like, yes, awesome. Yes. Okay, that deserves it. Hold on a second. That's awesome. Where did you just go? Sorry, I just want to personally. Yes, the left side is going to look like this. In fact, let me just spread this out. I'm not changing it, I'm just spreading it out a little bit. The left side is, and specific, and you know, truthfully, something like this. Right. This is, I mean, right. The left side, in other words, is natural log. Oh, natural log, because x is in the denominator. I mean, that's a thing. Now, that's a thing you have to know from calculus. I mean, you can't just figure that out. There's no way to just come to that. I shouldn't say there's no way. There is a lot of reasoning and depth behind this idea of the natural logarithm being the integral of it. But I wouldn't expect anybody to just figure that out. Like that's something hopefully maybe you remember from calculus. This is what we get. Now we do the same trick as we did Wednesday, which is, okay, I've got a constant on each side, but I don't really want to deal with all those constants. That's like very annoying. So I just wanted to get you guys used to this again. Soon we'll do this in fewer and fewer steps, but you know, I can do something like this. Right. This is all just a trick for collecting constants. And then, so I end up saying this. Right. This is what we have so far. Right. So we have natural log of x on the left side equals 5. Now we want x. We don't want the natural log of x. We want x. So we want to undo that natural log. We want to do the inverse function of that natural log. Again, this might be, in other words, we want to raise e to that side. Well, I guess what I'm saying is this. Just to remind you, like the natural log of x and e of x are inverse functions of each other. So if you do e to the natural log of x, what you get is x. Like that's by definition of exponents. We can talk about that more if you want, but that is the definition of an exponent, or the definition of a logarithm is that's the inverse function of an exponent. So I'm going to raise the left side to the power of e in order to get rid of that logarithm. I'm going to do the same thing to both sides. I'm going to say, therefore, that x equals e raised to that entire right side, 5t plus c. You see this? Are people with me so far? Like, this is looking mathy. I know it is math. Oh, cool. Yes, yes, yes. Awesome. We have this now. Now this is still looking sort of clunky, but we're getting there, right? We have X on the left side isolated by itself. We have T as the only variable on the right side. Now the right side, again, now please understand, please, if this is where the math starts looking mathy enough, to those of us that always start, it's very easy to, as this looks more and more mathy, to start, our brains start shutting down more and more for many of us. Some people obviously get more and more exciting and get more excited. And also for some people, this gets more clear as it gets more mathy. I'm becoming one of those people in my life where it's more clear to me if it's written as math, but it takes a while to get there, right? I do understand that as this looks more and more mathy, it can look less and less clear to a lot of us, especially with all these letters and numbers flying around. So let me just remind you where we are right now at this stage. The only variable on the right side is T. Everything else on the right side is a constant. C is a constant that we don't know, and E is a constant that we do know, like it's 2.7, blah, blah, but right, but they're both constants. So we are getting somewhere. T is the only variable on the right side, but I still want to break this down further, especially because I don't know what C is. So what should I do? One thing I can say from math, from log rules, and this may bother, but I believe that this is true, right? Just like right? I mean, just to remind you, like exponents work this way because exponents are just recursive multiplication, and multiplication is just recursive addition, if that makes any sense. Like just if you go back to basic examples, like 2 raised to the power of 2, which is 4, times 2 raised to the power of 8, right, which is 8, all together equals 32, which is to say 2 raised to the power of 5, right? But that's what powers mean. It's the number of times you're multiplying the thing. So e to the blah times e to the blee is the same thing as e to the blah plus blee. I'm just, again, in theory, we know this, but I'm just trying to explain why it sort of does make sense. But, and you can stop me, please do stop me. It is legitimate to stop me on any of this, but this is what I think we have so far. I'm saying we therefore have so far, and we can go back to that if you want, but I'm saying x appears to equal e to the 5t times e to the c. That's what we have so far. Again, why am I dragging this out? Like largely because I don't know what c is, and I have to solve for c in order to be done with this problem. So I'm going to go one more step. I'm going to say, oh, multiplication is commutative. So I can say this doesn't look like it's really doing anything, but right, e to the 5t times e to the c is the same thing as e to the c times 5t. But now why would I do that? Well, I'm going to do the trick that I did before again, because it's a great trick. I'm saying, oh, we now have this complicated looking function, x equals e to the c times e to the 5t. That looks like super annoying. I mean, it is annoying, but e to the c, like, well, e is a number and c is some number. I mean, they're both constants. E happens to be a number that is known by everybody, even if we don't remember it. C is a number that's not even known, whether I remember it or not, but they're both just numbers. So e to the c itself is just some freaking number that I could call c sub 2, right? Like c is some arbitrary constant that I'm trying to solve for ultimately. E raised to that power is some other arbitrary constant. I'll call it c2. But then by doing that, I can just call the whole thing c2, and then it's the only constant in the equation. So I'll just call it c, right? In other words, I'm saying, as weird as this looks, and this is where math and physics become fun, because it looks like I'm violating rules of math and physics. I'm totally not. I'm using rules of math and physics to do less boring math, to do less math and physics and get on to the math and physics I want to do. So I'm saying what we have so far is this. So now we really are almost done with the function that we're looking for. Very different kind of function from the other answer, but very similar procedure. I'm almost there. I have x defined it by its dependence on a bunch of numbers in t, but the one thing is I still don't know what c is. Well, I do what we did before. I recall the initial condition. I recall that we were told that x at t equals 0, and I know I keep changing my mind about this, but let's say it equals 7, just to keep it consistent with the other problem. Then, so we always need an initial condition to solve for the arbitrary constant, or put another way, well, I'll write this down in a minute, but the arbitrary constant that comes out of integration, the arbitrary constant of mathematical integration is the initial condition of a physics problem. I'll say that again more clearly in a couple of minutes, but you notice that we always use the initial condition to solve for the C, and the C always comes from not having boundaries on our integral. The C always comes because we have a supposedly indefinite integral. Indefinite means you don't know the boundaries of your situation. But the thing is, secretly, we do know the boundaries of the situation. They are the initial condition. The boundary of the situation is what's the value of the variable right at the beginning. That is the boundary of the situation. We secretly could have put that in the integral and made it a definite integral and not have to go through this. Boundaries of integrals are, boundaries of integrals are what solve for arbitrary constants of integrals. Boundaries of integrals come from boundaries of physics problems. In fact, I'm going to write that right now. It's worth it. What I'm saying is, okay, just to note, they're one and the same. The arbitrary constant that comes from not, we always get a plus C when there's no limits on the integration. And the limits of the integration, what they truly come from is knowing what's going on at the beginning or the end of a situation. And the initial conditions that are presented in a physics problem are what's going on at the beginning. So they make the definite, they actually make the integral definite ultimately, whether you use them at the beginning or use them at the end. Anyway, that's what I'm doing right now. I'm saying let's use them at the end. I'm saying right, so we just plug in 0 for t. That's what I'm doing. I'm plugging in 0 for t, knowing that it should yield 7 for x. And I'm doing that to solve for 7. So what is, I guess I'm asking everybody now, this is like a paying attention question or whatever. What is e to the 0? Anybody or everybody or anybody? This is totally 50 points. You can all answer it in the chat, whatever. E to the 0. If you just put the answer in the chat, it's 50 points. Yes, that is, yes. And keep going. Really, even if someone's already done it, just anybody who's like has a moment to wake up right now and get 50 points, it's like, yes, awesome. Oh, wow. Oh my God, that was like 20 of you. This is like such a class. It's amazing. Yes. Oh my God, don't forget to like and subscribe to this class. Yes. Okay, so we're totally clear. That's good. And I do mean it. Any one of you can now submit that for, in fact, since you put in the public chat, honestly, you can even submit this as an example of for right or for wrong, because any one of you could have been wrong about that. I mean, granted, there's a lot of you, but like, just so you know, but I'm pleased. It helps me to see this. So yes, e to the 0 is 1. E to the 0 is 1, which of course then means e to the 5 times 0 is 1, right? So we get, right, therefore, right? So end of the day, and speaking of end of the day, almost at the end of the day, this is a long, and this is again, I'm going to apologize again. I don't know why, but I know this is very mathy, not physicsy. This is all in the effort to study oscillation. And this is how the physics goes, is that we look at oscillation. It seems like a very simple situation. Suddenly we're like, whoa, it's simple, but it's not easy. It's a whole new branch of mathematics here that pops out of a spring. And that, again, is what happened in history. And then physicists together made up the math, as they often do, to make this work, which means it's make-upable. They didn't look it up. They did things that were reasonable, that they believed after they did them. That's what we're going to do. Again, okay. But what are we finding right here is we're finding then in summary, okay. Now, oh, I'm sorry. Okay, worth pausing here. The thing I'm trying to emphasize is we just did 2 exercises back to back. I mean, separated by 5 days, unfortunately, but the 2 exercises are meant to look near identical. They are nearly identical, these 2 exercises. The only difference is that one says 5t on the right side of the equation, another one says 5x, but everything else is the same. And we get an answer to each one of them by doing the same procedure really carefully. But we end up getting very different answers. And I mean very different kind of answers to each of these. I mean, they both have a 5 in them and they both have a 7. And that's not a surprise. That makes maybe sense. But these are 2 very different kinds of functions. Oh, sorry. And by the way, since I know this is taking a while and it always does, and I know class is over soon, I don't even want to fool anybody into saying that this exact procedure that we're doing here is going to be the exact procedure that we do to solve our spring. It's actually not going to be the exact same procedure. But what I am trying to show you is something very different happens when you apply that procedure to a differential equation from if you don't. Like the second situation, like the answer had an E in it. E is definitely more unusual or more sophisticated or more tricky, or so you don't see E as much in your life, I don't think, or I don't, as you see things like 5t squared or 5x squared or something like that. Like, or put another way, we've seen 5t squared, 5x squared before in physics, like with kinematics equations, like x equals 1/2 at squared. We've seen equations before where the independent variable is raised to a power. But we actually haven't seen equations before in physics where a power is raised to the independent variable, like E is kind of a new thing, and it is worth pausing on. The E expression in our second situation is not a power function. It's not what's technically called an algebraic function. Technically, an algebraic function is one where, is a power series function, like a to the x. An algebraic function is something like 5x to the 7th minus 3x to the 6th plus 4x to the 3rd minus x plus 7. Like anything where you can arrange all the x's in terms of descending powers, and you don't even have to have all of them, but whenever x is just raised to a bunch of powers, that's called a power function. We didn't get that in the second case. Even though we're just about out of time, but why? Why didn't we get it? Or what does it mean that we got an exponential? And are we going to get an exponential for the spring? Well, to cut to the chase a little bit, we're not going to get we might get an exponential for the spring. More likely, we'll get something that has cosines and sines in it, as some of you did definitely find out or figure out when you're doing homework 1. We're going to get an expression for x that is not a power function of x. We're not going to get something like x equals 5t squared over 2 or something. We're going to get something funky that has cosines or sines or e's in it because of the nature of the derivative. Remember we said we check our answer by differentiating. Like, let's do that here. Let's check our answer here. And probably that's all we'll have time for today, and it's okay. And remember, by the way, also, I want to remind you, before we even go back to the spring, notice when we're saying x equals 7e to the 5t is our answer, it's our solution. Like the original thing we're trying to solve is dx dt equals 5x. We're looking for a solution to that. A solution is something of the form x equals blah, 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 blah. Right? So right now we're claiming, and again, you have to get used to this, like numbers are no longer solutions for us. And equations are no longer the things that we solve. We solve things to get equations. Please bear that in mind. So right now we're saying that this equation, x equals 7e to the 5t, we're claiming, we believe we did things right, so that we're claiming that's a solution to dx dt equals 5x. Like it solves that, it fits that. It's a version of x that works for that statement about x derivatives. So let's just check it. Like, I think this is where we're going to end right today. Again, there's no new homework. There's like wherever you are in the homework. I know we have, in fact, I'm actually hoping to end a little bit early today, to tell you the truth, because something is coming up on my side. But can I ask you guys, as we're starting to wrap up here, just to see what's going on with the math? Again, I apologize. We have to bring it back to springs. I know that. But can I ask you guys as a class to check, like, can one of you, maybe somebody new if possible, like if this is our function here, right here, that we're testing, that we're checking, can somebody take the derivative of that with respect to t? Like, or I guess to break it down, does anybody, like, what is, well, yeah, actually, can somebody take the derivative of that, like if this is what x is as a function of t, what is dx? Oh, I see the chat. Cool. Yes. Good. Yes. Now I agree, and I don't know if that was private or public, but I agree with something I just saw in the chat. Yes. Cool. And I'm going to write that. Yes. So from the chat, what someone just wrote, and I agree, is they said, okay, dx dt is going to equal 35 e to the 5t. In order for them to get that, and that's right, that's a 5. How they got that, I believe, I mean, they must have, is they had to know two things in order to get that. They, wait. Sorry. Oh, and I should say, well, yeah, no, how they got that. So they're saying, what just happened? Okay, just to make again, oh, cool. Yeah, cool. Oh, that's interesting. Oh, yes. I'm looking in the chats. I'm just responding out loud. But yes. And again, this is public, everybody's at different places, but just to be clear, what's going on here, in order to check that derivative, and in order to check, you first have to use the e, you have to know. So like if you have a simple function, well, actually, sorry. Just reminding you that if you have this, just to remind you that e to the x is that one and only one function whose derivative is itself. That's an important, vital feature of e to the x. In fact, that's what e to the x is. It's the function which is whose derivative is itself, right? And you could consider that a memorizer if you want at the moment. Like, I'm not even really pretending to explain why that is, although that's fascinating, but it is true that e to the derivative of e to the x is e to the x itself. And it's also true that chain rule always works, right? The chain rule looks like this, if you like. This is one way to think about it. The way I always think of chain rule, because it makes sense to me, is you could think of chain rule as basically just saying this. It's, well, I'm just going to write it this. You all think of chain. I think you all know chain rule, but I'm just saying here very quickly, and we actually are going to leave early in a moment, but I'm saying here. Here, if you want to take the derivative, you have to use the e rule and the chain rule, like the derivative of e to the 5t the derivative of e to the 5t is e to the 5t times 5. That's what I'm trying to say up here by chain rule. So this equals 5 times 7. That's where he got it. But the important thing here, since we are wrapping up, like the important thing is that all of a sudden E is coming into our life. All of a sudden exponential functions somehow seem to be important, or some kind of funny functions. Like what I'm trying to say is, we will pick up on this on Wednesday, and there's nothing new for you to do with this or anything Wednesday. Just keep on keeping on. But what I'm trying to say is, algebraic functions, power functions, like x equals 1/2 at squared, or here x equals 5t squared over 2, something like that. Any function like that where the variable is raised to any power. Okay, I'll write this. With any power function, like 5t squared over 2, you take one derivative of that and the power goes down. You get, you multiply by the exponent and then you lower the exponent. So you all know the derivative of like 5t squared, the derivative of that is 10t, and the derivative of that is 10, right? And the derivative of that is 0. No matter how high that power is in the function, no matter how high the exponent is, as long as it's a finite exponent, after a finite number of differentiations, a finite number of derivatives, you will eventually get to a derivative of 0. No matter how complicated the function is, if it's a power function, eventually there's some rate of change of it that stops, that there's some level at which the rate of change is not changing. And so something about that thing will be constant, some derivative. But anything that's described with like an e, right? E to the x, you take the derivative, you get e to the x. Take the derivative again, you get e to the x again. I don't even care if it's e to the 5x or 7e to the x. If you take the derivative, you get back e to the x. No matter how many derivatives you take, you never get nothing. That's a totally different type of function. That's a type of function that we're going to need to describe this spring. We're going to need some kind of function where when you take derivatives, you don't eventually get down to 0, where you can always take derivatives. Why am I saying that? And we really are going to stop on this. Just remember, in the back of your mind, remember we said that this thing, when it's coming in, the position is increasing. Sorry, as it's coming in, the position is decreasing, the velocity is increasing, the acceleration is decreasing, the jerk is increasing. When we think about it intuitively, there's not any intuitive reason to expect that any of those derivatives would ever stop changing. Or at least I think that's the pattern that we're seeing. And so we're going to need some kind of function that captures that. 1 of at squared, 1 of at cubed, 1 of at to the 7th will eventually say that some rates of change are not occurring in this motion. And I believe they all are. I'm just going to, that's a lot. I'm just going to leave it right there for right now. I mean, in other words, I'm saying we get an exponential function. I am saying that, just in short, I guess I'm saying this. Okay, technically an algebraic function is the word given to a function that has a finite number of power terms, like I was saying before. And I just want to say right now that we have to deal with some differential equations here for this. We have to deal with a differential equation to describe this spring. And there will be others down the line in this course. Whatever the solution is to it, and of course, many of you already got it in your homework or got it with help from the web, all fine. But whatever that solution is, I'm trying to reinforce right now, it could never, would never, ever be a power kind of function. We need a solution that can be differentiated somehow forever. And that's what we're going to find. I'm going to pause right there. It's a little bit, oh, it's not even really early, but I do actually need to, if I could just get, I can't really stay for like actual questions right now. I apologize, or today, but if you guys are basically good, if I can get any kind of goodbyes, then I'm good to say goodbye. And I'll post all of this, of course. Oops, sorry. I will post all of this, of course. I'm good if you guys are good.
Thank you, Professor.
All right, I'm good. Thank you, Professor.
Thank you very much. Thank you. Awesome.
All right, have a great weekend.
You too. Great weekend.
Oh, great day.
Okay.
Great day.
Okay. Thank you. You too, guys. Okay. Bye. Bye. Thank you guys very much. Okay. Awesome. Bye. Awesome. Thank you. And you're good, Brian? Hello, Brian. Good. I'm going to assume good.